So our group worked on a conductive liquid level sensor, and we are Matt, Chris, Adam, and Theo, and our advisor is Dr. Cho. So an introduction to our project, the current market value is around $4 billion, and it's set to grow around 50% for the next 5 years. Out of the three sub-markets, the largest one is the industrial market. And the things that the stakeholder was asking for was to make an economical, more affordable product that they could afford to buy and install in their plants. It was easy to install and to put in new tanks. Had different alerts set up. So if it started running low or getting too high or dropping too fast, an alert would go off. And also it would be Wi-Fi capable.
So we decided to break this project up into 3 different phases. Each one would coincide with a new quarter change, fall, winter, and spring. So for the first quarter, we decided to work on the proof of concept in our prototype 1, which is shown with the copper wire extending down to the bottom of the beaker and then connected to 2 alligator clips. And then the second prototype that we worked on was a 3D printed probe that would sit in the bottom of the testing beaker, and then that would go back and forth distance-wise with 2 strips of copper wire tape. So we could also add another variable to the testing apparatus. And then our third phase of the project would have included Wi-Fi capabilities as well. So for our major requirements, we wanted it to be scalable to accommodate different environments, whether that would be a distillery or a chemical plant. We also wanted it to be minimally invasive, so relatively easy to install, and then also low maintenance, so workers wouldn't have to come in every 5 years and replace it. And then we also wanted a digital output display. This would just make reading the liquid level easier, and it would just make the data more useful and easy to see. And then we also wanted it to be Wi-Fi enabled, so we could connect this up remotely to a central computer system or a mobile workstation to access several different tanks at once.
So there is no set of standards for liquid level sensors. They're normally tested and refined by the manufacturer. And so the standards that we're using for this project are for our test methods and our electrical components. And they consist of the standard test method for electrical conductivity and resistivity of flowing water samples, and 2 IEEE recommended practices for software requirements and system Verilog for unified hardware design.
So in order to achieve our major requirements, we split our project into 3 separate phases. We were able to complete 1.5 of these phases. So the first phase was our proof of concept test, which we did with our first prototype, and that was just to verify the efficacy and the validity of our project. Phase 2 was to take feedback from our testing in phase 1 and apply it to the design of a second prototype. We were able to produce our second prototype, but we weren't able to test it. And our phase 3, which we did not get to, was to implement wireless capability into our sensor. All of our prototypes incorporate one design theory, and that is we create a circuit with probes that don't touch, so it's not completed, and then our working fluid completes our circuit. We have an input voltage and current defined from our voltmeter, and that goes through our first probe, propagates through the working fluid, and goes into our second probe. And depending on the voltage drop, we can determine the resistance in the fluid and calculate the volume. And then with tank or container dimensions, we can calculate liquid height.
So here's an image of our circuit design. On the right, on the bottom right, is our Arduino Uno, which is the central processing unit that we're using. On the left is our prototype 2 setup with the 5-volt input coming in from the Arduino and the voltage output or input going into the Arduino. So we're using jumper wires, alligator clip connections to connect to the prototype. And from there, we'll be using copper tape to go into the tank. And above the Arduino on the top right corner is our 16x2 SunFounder LCD display. And that display in particular came with a bus to help reduce the amount of connections, and it actually reduced the connections of analog inputs from 4 inputs to 2 inputs, which greatly reduced our circuit design. And here's an image of our sample code, which includes all the code that we used for the Arduino Uno and its processing itself. The 3 most important lines of code are in the middle, and 3 of them start with double, and these are used to represent the equation relating liquid level and resistance.
So our first prototype that was used in our proof of concept was its copper wire connected to a piece of generic scrap plastic, and this particular one was warped in the picture due to testing. And then at the top, the wires are attached to alligator clips that connect to the multimeter, and that provided our input voltage and also calculated our resistance through the circuit. It's sat against the wall of the tank, and some of the benefits of this were that because it was so simple, it was easy and cheap to make and produce, and it was disposable. So we could use one sensor, test it to failure, and then make another one for a new test with no risk of error carrying over from a worn down or dirty sensor. Our second prototype was 3D printed from an SLA resin, and we made the model in Creo. And the 2 parts of the body slide in and out to adjust the distance between the probe, which we had planned to test, but we didn't get to. And we replaced the copper wires with strips of copper tape, which provide more surface area to propagate current through. It sat against the wall of the tank like the first one, but we had feet incorporated into the bodies so that it sat nice and flat on the bottom. We had planned to incorporate wireless capabilities, but we didn't get to it. So present technology uses analog systems like SCADA to receive data from tanks, and it's quick, but a big drawback is there's limited access points because it has to be hardwired to one control panel or computer, and that really affects the accessibility of data and other information that's presented at those panels. So we proposed being able to access data that's transmitted wirelessly from our sensor to a computer or a mobile workstation. It allows for just greater accessibility of that data. You can monitor multiple tanks at once, and you can do all of this remotely. And as I mentioned, we did not get this done due to restrictions.
So on the right is a graph of our Jack Daniels average values. These average values come from the 3 runs that we did with Jack Daniels, and these are just the values averaged over. These results are from our testing in prototype 1, and it shows a curved relationship between resistance and liquid level. And we found that the best regression curve for this set of data was an exponential regression curve, which you can see the equation on the slide here. And we're hoping that prototype 2 would have been able to support these findings.
So for the materials that we use, we were able to use some as prototypes and also some to record data. So the digital multimeter, scale, pH meter were all used in data collection, as well as the 2-liter beaker. The Arduino and LCD screen were going to be incorporated into the final product in order to have a more finished look. The copper wires were used along recycled plastic for the first prototype, and the copper wires were used as the conductive material in order to get the measurements. The copper tape and the SLA resin were what the second prototype consisted of, and using the copper tape versus the copper wires we were able to produce a better surface for the conductivity. So the fabrication methods that we were able to incorporate was mainly 3D printing, and the 3D printing was what the main body of the second prototype consisted of. And we wanted to use an SLA resin because it was going to be more resistant to any corrosion or wear from the different fluids that we were testing. We were going to make a custom housing for the electronics above the tank using CNC, but we were never able to incorporate that into our design. We were able to use a soldering iron to solder some of the wires together on the circuit board, as well as the wires going to the prototypes to make that more sturdy and have a better connection. So the testing methods was the main crux of this operation in our testing. So before we tested any of the fluids, we take the temperature of them, the pH, and we do that each run. So we have 3 different temperatures for each fluid. So after that, we would zero the 2 liter scale, the 2-liter beaker on the scale, and that would be what we would be testing and pouring the fluids into. We would use a large syringe. We'd try to go and put 100 milliliters of whatever liquid we were testing into that beaker. We let that rest for around 30 seconds. And after 30 seconds, we would record the resistivity off the ohm meter, as well as taking down the weight of that fluid. We would use the weight instead of just the volume, because the weight would be more consistent, because that's a digital measurement versus just looking to see where the plunger lines up on the large syringe. We will do that until we have 200 milliliters of that fluid in the beaker, or until the fluid is out. Some of the fluids that we tested didn't have exactly 2 liters that they came in. So if we ran into that situation, we'd end wherever we ran out of fluid. After we did reach that stopping point, we'd put all the fluid into a different container. We'd rinse out, we'd wash the beaker, dry it off completely, as well as wash and dry off the prototype. And then we repeat that 2 more times for each fluid.
So some of the software that we used for the liquid level sensor is Creo 6.0. We used it to 3D model images of our prototype for rendering images. We also 3D printed our prototype 2 using Creo as well. We also used Arduino IDE, which is a C++ programming interface for Arduino. And we used it for the LCD screen and for automating liquid level readings. And finally, we used AutoCAD, which was used to create accurate 2D circuit diagrams.
So the 4 major impacts that we were told to assess were economic, environmental, social, and ethical. So the main driving point of this project was the economic availability and impact that our project could do. So the current market is at $4 billion. It was set to grow around $6 billion in 5 years. So with such rapid growth, there's room for a new product to come in and take some of that market space and be able to produce a product that can make money. Also, environmental impact we thought was important because a lot of tanks aren't monitored consistently. So if they do end up leaking and they're not monitored, no one's going to know until the next person comes over and checks on a tank. So one of the things that we wanted to incorporate was the ability to detect a rapid change in the height or the volume of the tank. And if we were to do that, we can incorporate that into our product. So if the tank ends up leaking and lowering at a rate faster than it should be, we'll be able to alert the operator and they could stop that leakage before it had a greater impact. The social impact that we thought that was the main thing that came out of this project was the remote readings. So if the tank was in a closed area, which could increase the hazard of going into it, or it could be an area with an engine room or something along those lines with poor air quality, like that would be something that an operator wouldn't want to go into much. So if we had remote readings, they would limit the amount of times they had to go into those closed areas or areas with poor air quality, which would make their job a little bit better. So the ethical impact that we could see coming out of this would be, since due to the automation and not as much need for operator to check on the tanks physically, there could be some sort of job loss. But the other three impacts, I feel, outweigh that potential job loss due to automation.
So here are some of the results we obtained from our testing of prototype 1. We found that the Jack Daniels that we tested proved to be one of the most accurate of all the liquids we tested. As you can see, all three runs line up with one another when looked at mass versus resistance readings. And then to the graph on the right, the Jack Daniels compared with resistance versus the liquid level is shown to have an exponential regression curve. So we had pretty good data with that. Other liquids we tested included Coke, 3 different types of milk, alkaline water, beer, liquor, and apple cider, seen here in these 2 graphs. The graphs of the apple cider shown here display some of the errors we encountered, including a dip in the resistance value, which could have been from extraneous interference. And then we also encountered a few other issues, such as with the carbonated liquids. They slowly lost their carbonation over the period of the 3 runs. And so that was a variable that we could have looked at a little bit more. And then we also found that with the increasing temperature of the milks, that created offset curves. So temperature was also another factor at play here.
So as we said before, we weren't able to complete all of our work. We were able to complete prototype 1 and do our proof of concept testing, and we were able to take the feedback from prototype 1 and create a second prototype. Another thing that we were able to complete was the software and developing a real-time feedback loop, as well as connecting that to an LCD display to show our data.
So looking back on our project, the few things that we were able to do well was produce a large amounts of data collection from our first prototype. So we were able to collect over 300 points for the 8 or so fluids that we tested. And with those data points, we were able to produce over 20 graphs that could show the consistency of our product and prove that the concept was a valid concept. So some of the challenges that we faced was the voltmeter is always changing over time. So that's why we had to pick a certain time to take a reading from it. So that was an obstacle that we had to try a few times to figure out a time that worked well without creating a project that took hours and hours to record a few data points. Also, our product didn't have consistent readings when the volume was lower. So around 500 milliliters and below, the readings are they changed drastically compared to the rest of the data collection. So we had to change our graphs accordingly to show that after that jump, that the graph leveled out and was more consistent.
So we learned a lot of lessons while doing this product, but three of the main ones were, first, that we'd like to have a product with less volumes so we don't displace as much working fluid, and this does affect our measurements, although we weren't able to determine exactly how. It was just an offset in the curve. Another thing that we learned was that testing takes a lot longer than we anticipated. So we had to test more experimental variables and conditions than we expected, and not only that, but testing itself just took a long time because of how our voltmeter took measurements, just what actually went into our experimental process. So we think that we could have divvied up the work for this better and to use our time more wisely. Another thing that was interesting that we learned was that there's an alternative way to calculate the resistivity, or the unknown resistance in the fluid, and that's to use the equation R for resistance is equal to the ratio of the length to the area, this is surface area of our probes, and that times the resistivity would give us our resistance. And resistivity, which is rho, we found by taking the inverse of the conductivity of the fluid, which is just an innate property of that liquid.
So here's some of the recommendations we would go if we had proceeded with this project. The first one would be to start testing earlier in the term. We discovered the testing took a pretty long time with having to clean out the container and wait for the voltmeter to give us the data. So we would start testing much earlier. Also, we would have liked to test different probe materials, such as stainless steel or any other material that would be good with conduction. And then also different input voltages to determine what best data to collect. We would have liked to figure out a relationship between how much probe contact with a liquid and the corresponding resistance values. And then also, we would like to get an image of the final product, not just the prototypes that we made, so like a completed product with LCD screen and the Wi-Fi capabilities. And then also exploring many other sensors to add on to the end of the project.
So in the next two slides are our bill of materials. We'll be talking about that more in the budget section, but one important thing to note is that we're able to save a considerable amount of money by using previously owned equipment and borrowed equipment from Drexel. We're able to borrow the Arduino Uno, breadboard, and resistor from Drexel, and we had previously owned the digital multimeter, pH meter, and we would have been able to borrow the soldering gun from Dr.Cho. And so all of that amounts to a considerable amount of savings.
So as Chris mentioned earlier, most of the materials that we had, we either were able to get for free or from other of our group members. So our total cost only came out to just under $120, which was below what we had anticipated. We were also able to save around $110 due to the pandemic. That would have been add-ins that we would have created if we had completed this project. And our advisor was fully funding this project throughout the term.
So throughout the course of this project, we've done quite a lot. We've experimented a lot. We've designed prototypes and experiments. We've done a lot of research, and we've networked with people for ideas and inspiration. And through this, we've all improved independently. We learned skills, including the ones I just mentioned, and we also learned some technical skills like experimental procedures, programming, and even using a soldering gun. We were able to apply our strengths and use them to our advantages, and we were also able to work in areas where we weren't as strong in order to improve there. And when we worked together on parts of the project, we each helped each other out, and we learned a lot of stuff through each other. And we even learned ourselves by teaching others. And we had fun. We explored a lot. We worked together on a lot of our experiments, so that was fun, and it went very well overall. Here's some of our references, and thanks for watching our presentation.